Hello, I'm Will. Welcome to ResearchPod. Quantum computing is quickly progressing from an idea out of science fiction to an ever nearer technological reality, and its applications seem almost boundless. However, the bounds of those applications, and of the very atoms involved, are real, with research bridging quantum energy, uncertainty, and newly discovered limits of just how fast a quantum computer could get. Today I'm speaking with Dr. Ness about how his research into quantum speed limits opens up new understandings of the cutting edge of physics. Dr. Ness, hello.
Hey, Will.
Thank you so much for your time and joining with us today. For a little bit of reference for everyone at home and for me as well, could you tell us a bit about yourself, your work, your research, and some of your academic path that's led to where you are today?
So I'm from Yoav group. It's the Technion, Haifa, Israel. The work that we're about to describe today, this is one of the subjects on which I focused on my PhD studies, which is quantum speed limits. And the experimental setup in the University of Bonn offered us a unique platform to really push the limit on how far experimentally can we study.
Now, I've got to say, the phrase pushing the limits on experimental studies of quantum speed limits is one of the most sci-fi kind of sentences I've heard in a very long time. And I've got to know, how does it feel personally to be working at the very cutting edge of how we understand how the universe works?
Well, always when you are zooming in to the work, you feel like I have this very little riddle that I want to study. But of course, it fills you up with very great enthusiasm when you zoom out a bit and you realize that your work or your day job is basically measuring something, usually something that had never been measured, and then trying to baffle with it, and it doesn't make sense. And you try to take it to collaborators and, working out a bit from all directions.
Zooming out from that riddle, to put it from the micro scale to the macro scale, how are you kind of connecting those tiny, tiny measurements with the rest of the world around you, perhaps?
Yeah, so the pleasure of working with the systems that we work with, which are basically ultra-cold atoms, is that they are maybe very complicated experimental apparatus, but in some sense, they are very, very, very simple. So we take atoms, which are the fundamental elements of this universe, and we play with them really, really gently. And this actually gives us the ability to do simple manipulations and study general properties of, objects around us.
I mentioned some of the international collaborators you've had on this project, and I've seen, looking over your profile, that you've been presenting at conferences all around the world and winning awards here, there, and everywhere. How would you describe the international community working in quantum speed limits and quantum computing?
So basically, it's really a great place to be in academic terms. Just a wide variety of fascinating people to learn from and share with your findings. But mostly, even this specific concept of quantum speed limit, even within this community, it's very fundamental on one hand. And on the other hand, its previous experimental research was quite narrow. So I feel quite lucky to present this kind of concept within physics conference, and I received quite a bit of attention. And, it was really nice to find interest for other physicists to learn about this issue.
Okay, and to be a window for the audience and for myself as we get into the details of your work, maybe we can start by, opening up the scope of the interview and setting the scene with why, out of everything in the world, out of any other topic in physics, out of any other topic in science, why quantum computing? What is it that matters about this work to you, and how you think that matters to the world at large?
Well, the first motivation, I would say, even not mine, of the founders of Direction, is that quantum computing on a very fundamental level is simply hard. It's really, really difficult to try to simulate a quantum phenomenon on a classical. In fact, we are very limited in our abilities to. So, nice idea due to Richard Feynman was, well, maybe don't try to hammer this with a lot of computation, a lot of classical computation, because it's really intractable. but let's try to build some machine which could be a computer that is based on these fundamental principles of quantum mechanics. And this is, of course, not an easy task to make, but the prospect of building such a machine are really endless. They can really lead us to learn a lot about our world. And also on the computational sense, they feature great advantages over classical computing. So this is something which really drives you to, hit this riddle.
Well, let's get into some of the details of your work. We should probably lay a good foundation in terms of some of the language that we're going to be using to discuss quantum computing and some of the terms that go with it. So, in observing and measuring quantum phenomena, like you say, there is the whole measure of uncertainty, which some people at home might be familiar with as an idea. We're also going to be talking about qubits, gates, and energies. So if we could just get a glossary of terms to start with, and then we can use that to explain the work that you've been doing.
Sure. So let's start with classical objects, which is what we are more familiar with, and try to grasp the concept of uncertainty. So in classical systems, uncertainty is usually a measure of cluster of objects. Let's take, for example, this pencil. And if I take one pencil out of my drawer and measure it, it's about 10 centimeters long. And I pick another one and it's just a bit more, and the third one will be a bit less. So I can say that the average length of a pencil is about 10 centimeters, and I have some error or some uncertainty of few millimeters. So if I don't know a priori what's the length of a pencil, I have some uncertainty of its length. So in the classical world, this is a property of distribution, of cluster of objects. In the quantum world, we can have this distribution within a single object. So let's say that we have a quantum pencil inherently feature several lengths. So it might be 10 centimeters, 11 centimeters. And once we perform something we call a measure or a collapse of its wave function, then we set on a specific length. But this distribution, this uncertainty of length of any other measure, is something which is inherent to the quantum object.
And then when it comes to qubits, gates, and energies, there was a lovely blog that came up through some of your other work about marbles in a bowl of light that kind of illustrated them in a very poetic and visual way. But if you could explain it for our audience listening to this now, what some of those terms mean as well.
Yeah, so let's start with the qubit. Qubit is basically the fundamental building block of quantum computers. Qubit is it's the quantum equivalent of classical bit. So in quantum we have qubit. Bit means that you have two values. You have either 0 or 1, and same goes for qubit. It has either 0 or 1. Let's call them red and blue. But what's special about qubits is they don't only have this 0 and 1. You can also have like 50-50. So the particle can split between the two, or any other population of the two, but it's not like, as we said in the earlier example, it's not a property of distribution of particles, but it's actually the very single particle that has superposition, or being at the same time at the two states.
So between the 0 and the 1, we're not talking about a measure of 0.5, but 0 and 1 at the same time.
Exactly. And if you will repeat the measurement many times, then you will find that some of the times it will be 1 and some of the times it will be 0.
Mm-hmm. Okay, and then the gates part of that.
Yeah, so now you have these qubits, which you say are like bits but have more fancy properties. You want to pass them just like in an ordinary computer. You want to harness these features and perform computation. So how do you do computation? You say, okay, I have here a few bits. This is 0, 0, 1. If the fourth one is 0, make it 1. If it's 1, keep it, and so on and so forth. So quantum gates basically perform the same act, just that they can even play with the inner probabilities. So we can say if we have an atom which is 80% at 1 and 20% at 0, flip it around, or some other manipulations that you can do. And basically these gates allow us to perform computation. Now, when we perform a sequence of gates, this is basically computation, right? Also in the classical sense. And this sequence of gates can be characterized by something we call a distance in the quantum. So if I want to ask what is the speed of quantum evolution, I can think of some computation which I will define as a D, and ask, well, how long is this? And also, how long does it took to execute all these gates? So what's the time? And as we remember from elementary school, you take distance divided by time and you get velocity or speed. And this is basically the speed limit, the quantum speed, the amount of computation you do divided by the time.
In my head, I'm picturing this as like a series of, I watch on YouTube the Marble Run Olympics, where a guy's like pinging marbles down like long runs of tubing to like basically come up with an Olympic table of how fast his marbles are moving. It's ridiculous. It's absurd. I love it. But this is how it's kind of visualizing in my brain.
It's not that far.
And lastly, the idea of interference.
So interference is maybe the most fascinating phenomenon about these qubits or quantum. And this means that we have these different distributions or population of states within superposition. So each atom, each particle, each object has like non-deterministic state. And we can perform manipulations, for example, gates, that actually share information or make two of these objects interact. So interference is the act when the populations or probabilities of one quantum is affecting the population of another one. And together we can extract some useful information about the relation between.
And with all of that said, do we feel like we have enough covered to start addressing your particular experiments?
Maybe just to relate to our previous example of the length of the pencils, I will just emphasize here that what we are interested in is actually energies of levels. So if we have 0 and 1, for example, it casts to two energies, so two values of energy that the atom can be in, or particle, or whatever, and it can even feature more level than only two, so going beyond the Q regime. That's basically what we did in the experiment, and why the results were so interesting. And the reason we are interested in energies and in the uncertainty of energy and the mean value of this energy is that these values would dictate the quantum speed limit, as we will see.
So, with the establishment that there are speed limits, could you tell us what part those speed limits play in the setup of your experimental observations, the lasers, traps, and cooled atoms part of things, like the physical operation, how you are making these observations and doing these measurements?
So we are using cold atoms, which enable us to study very carefully this evolution of the quantum state. And these atoms are actually extremely cold, just to give some kind of a feeling to how cold they are. So it's worth mentioning that there is an absolute zero temperature in this world where everything kind of freezes. It's about minus 300 degrees Celsius. And in this scale, we can talk about how much we are hotter and colder than other objects. So, for example, we are 20 times colder than the surface of the sun, more or less. And if we can think about liquid nitrogen, for example, something like widely known but still very cold, then we are something like only 5 times warmer than this liquid nitrogen, while our atoms are something like 50 million times cooler. So they are really, really extremely cold. And the reason we go over all this effort and make them so is that in this regime of temperatures, instead of fizzing around like the atoms in the air around us in a jet plane speeds, they almost stand still. So we can really delicately study them. So we kind of get rid of all this thermodynamic motion that we are not interested in.
Mm-hmm.
So these atoms enable us to study very carefully the bounds, and we can also create very precise potentials that hold these atoms. By these potentials, which we can analyze their energy spectrum or their energy landscape, we can execute measurements to probe these quantum speeds.
Now, the probes, those measurements that you mentioned, I believe the term that I've picked up from your papers is a fast excitation interrogation scheme. Is that right?
Yeah, so I think I will not dwell too much on the technical term, but what's the essence of the experiment that we did is that you want to study dynamical properties of these quantum systems. And this is non-trivial. Usually when we think about quantum entities that we want to measure, we arrive at some final state and then we want to characterize. And here we try to characterize some motion. So when you try to capture dynamics, you need your probe, you need your measurement tool to be much faster than these dynamics, or much finer at the temporal scale. So we made an effort to execute these gates, these interferences that we induce on the atom on a very fast time scale. The time scale of evolution that the atoms undergo in these experiments are something on the order of microsecond, which is basically 1/1,000,000th of a second. And what we did is build on Raman transition, shortly elaborate on, to execute these gates in something less than 50 nanoseconds, 1/1000,000th. So to give some sense of these Raman transitions, so vital to this experiment, so the usual way to translate atoms between two states, the two states that we are interested in here, is using microwave antenna, just like the microwave antenna used to warm up your lunch. But if you want to drive transition fast with microwave, you would probably need to invest so much energy with this direct transition that you will cook up the whole institute. So if you would like to avoid this, you could use this Raman transition to utilize light. And this light is something that we can focus directly on the atoms. And by this, we can induce very high intensity or very fast gate rate directly at the position that we are interested in and implement this fast transition. I just want to say that basically these Raman transitions are the physical reason for me to move to the University of Bonn for active collaboration of a few months there in order to actually construct the optical system to perform this kind of Raman transition. And in this context, I would really like to acknowledge my partners, especially Manolo Rivera Lam, who worked with optical setup, and the other teammates which made this.
You said quantum state evolution a couple of times there, and that is the state of approaching certainty within the bounds of between 0 and 1, or the movement from one state to another. Yeah, with the scale of temperatures that you've set there, somewhere between the sun and absolute zero, it'd be nice to think that you could use those cooled atoms for a functional purpose, and that's what your experiment relies on, is having them and using them to make those measurements, right?
Yeah, so basically we take these cold atoms, and the reason we executed this experiment, the specific laboratory at the University of Bonn, or what the specific feature that their experimental setup is offered, is something which is called a spin-dependent optical lattice. By that, we mean that we have some potential, which we can imagine as some hill or some slope that the atom can roll along. And this potential is actually different to different states within the atoms. So if we imagine our two states as red and blue, we can think of the atom split it into two marbles, these two colors, and we have a red slope for the red marble and the blue slope for the blue marble. And now, because we can position them separately, what we can do is we can prepare the atom at a position which is at the bottom of the blue slope. So the blue part of it would stay still, while it is on the top or somewhere in the middle of the red slope. So the red marble or the red part of the atom would roll down the slope and evolve in time. That's what we mean by evolution. So here we try to capture it, to imagine it only as a physical evolution, like mechanical one, but it captures most of the essence of also the quantum world, which is just slightly more complex. And then when we say evolution, we kind of ask how far does the red marble went? And if we want to ask how far did it went, we need to somehow compare it to where it was. But because these are quantum states, we cannot measure them twice, right? Because these are very fragile states that will collapse if we do. So that's why we invoke this blue marble to begin with. The blue part of the atom would stay still and serve as a reference for the initial state. So when we compare the two parts by executing another interfering gate, we can actually learn something about the evolution of the evolving part throughout this.
Now, your work builds on a couple of decades of prior research into quantum mechanics, quantum computing, and quantum state evolution. So, to kind of backtrack a bit and kind of fill out the theory of what has led to your work on quantum speed limits and the experimental setup that you've described, there's some names and some Nobel Prizes that would be good to appraise the audience of. The previous limits that have been set on quantum operations include those of the Mandelstam and Margulis-Levitin bounds. So could we cover what those bounds are, those limitations on quantum observations, and how your work on speed limits kind of fills out the next stage, the next part, the unknown area of what has been previously researched?
So the basic question of quantum speed limit is, well, how fast can a quantum state evolve? And the first clue that we have towards answering this question is something called the Heisenberg uncertainty principle. Heisenberg uncertainty principle is almost a mathematical principle, although it's a very fundamental element of quantum mechanics, which relates uncertainties of different measures of conjugate variables. So, for example, if you measure the position and momentum of a given particle and do it simultaneously, your uncertainties ought to be greater than some constant number related to the Planck constant. And this can also be translated into energy and time. But this yet not provide you with a solid or very refined limit on how fast the evolution can occur. It just gives you the correct time scale. And what Mandelstam and Tam did back in 1945 is that they formulated the relation between the energy uncertainty and the rate of evolution. They said, okay, given this and such uncertainty in your energy, the fastest way a quantum state can go from point A to point B is given by some formula. Later, another bound was found by Margulis and Levitin, which related this minimal evolution time to the value of the energy itself, so to the average value of the energy. So we see that we have these two energetic values, this average value and the energy uncertainty, and we have these two limits due to Mandelstam and Tam and due to Margulis and Levitin that constrain them and relate them to the fastest speed that can be undertook by a quantum process. And these are, of course, two theoretical results. What we offered is an experimental observation of these two bounds.
And a third bound that will it be known as the Ness limit from now on?
I highly doubt that. Before we go to the third bound, there is one thing else that we should mention. An interesting aspect of these two limits is that actually they have different functional form. What do we mean by that? Importantly, we said that we have these two bounds, one related to the mean energy and one related to the energy uncertainty. And now you can ask me, okay, but what is the speed limit? So the speed limit is given by the most restrictive of the two, right? Every time one would be more restricted and it would provide the bounds. But interestingly, these two limits don't evolve in time at the same functionality. Namely, if you have, for example, energy which is greater than your energy uncertainty, the Mandelstam bound would always be the dominant one, and your evolution would be governed by the Mandelstam bound. On the other hand, if the energy is lower than the energy uncertainty, then we would see two phases of the evolution. First, the quantum evolution would be restricted by the Mandelstam bound, as it was in the other case, but then only at non-initial times, it would translate to be restricted by the Margulis-Levitin bound. So you have two distinctive dynamical regimes to explore.
And how does the new bound that you've discovered fit into that picture?
These are the dynamical regimes that we were probing in our experiment, and we found out that there is something very asymmetrical in this picture. So for most practical applications where we actually make the system, there is an inherent upper bound on the energies. By this I mean that you cannot have any value for the energy, although we have distribution because it's quantum and it's unknown and everything, there is still some cut where you say, okay, I cannot have energy greater than this and that value. And if you consider this energy, you find that even if you just randomize an arbitrary state, it's almost all the time fall into the milestone time regime, this single time scale. And this was not clear why this is the case. Then we thought, okay, but if you flip the world around, so you make this ceiling, the top energy, being your floor. So you just invert all the energies. You find out something really nice. You find that there is something which is like the Marius-Levitin bound that was before to the very small energies that were near the floor of your energies, but now this, what we now call floor, is the ceiling, right? So basically, we found another bound which is like the Marius-Levitin one for these high-lying energy values. So for states that have energy which is close to the top available energy, there is a third bound, which is very much like the Marius-Levitin bound which we have for the low-lying and near the ground state. So in some sense, by analyzing this picture and observing this asymmetry between the two bounds, we discovered that there is a third bound to be addressed, and this bound, we call it the dual Marius-Levitin bound because it's kind of dual to it in its form. And using these three bounds, we have a unified picture of quantum speed limits, which is very useful because what it gives you is actually, by utilizing very modest knowledge of the state, so you only need to know the energy and the energy uncertainty and maybe the energy from the ceiling, you get some bounds on the rate of evolution, which is something information-wise is very, very expensive. So in some sense, these quantum speed limits and the exploration of quantum speed limits helps you a lot when you try to draw estimations about complex quantum calculations.
With that new bound, that new limit in mind, is it too soon, either in this interview or in your research, to start connecting that back to quantum information applications like data storage and, the process of computations?
So I would say that quantum speed limits are very, very readily connected to actual applications, computations. The little caveat about it, I don't know if caveat is the right word, but is that the quantum computers that we have now, we are able to fully simulate it. So why draw bounds for something which you actually know what its velocity? But I hope that in the near future we would have these quantum computers which we cannot simulate classically, and then the quantum speed limits can become really handy.
So you're ready for the next generation of that processing?
Yeah.
Or, the future eventual. Maybe not next generation, but next.
Yeah.
Well, with this, like you say, information in mind that's already being used, are there any other old experimental data that is changed or challenged by knowing that there is this third bound? Is there anything that needs to be revisited in prior research?
So yeah, in some sense, our previous experiment was only executed having the two first bound. No one has revealed them at the point of the experiment. So given this new bound and this new regime that measures have three bounds now, there's room for additional new experimental evidence that can demonstrate the links with similar techniques or by inventing new techniques.
Do you have any next steps, next research, new avenues in mind for how you would explore the adjacent space around this?
Yeah, so basically related to these third bounds, as I said, you can more or less execute the same experiment and just study this new bound. But more generally about quantum speed limits, I would say that a very interesting problem or very interesting direction to explore is something called open quantum system. So in the description that we ran today, we focused on a quantum system that we completely know how to describe. So it has this and that distribution. Its distribution is fixed over energies until you measure it. But in reality, we almost get to this case with our very cold atoms, but in any other platform, you always have some interference from the environment or some distorting interference, not the one that you like to have. And this interference can lead to very different dynamical evolution of the system. So there are already some theoretical attempts to construct, to formulate bounds for these kind of open quantum systems. And I would say that maybe the most interesting thing to do in experiment now is to experimentally probe these speed limits in open systems and see how this openness or relation to the environment of a system can relate to the quantum system.
To cast a wider view, a longer view over maybe the next 5-10 years, the next few maybe generations of computing, where do you see this research going, fitting into the larger research environment, the international approach to quantum computing research? If there's any step beyond the next step that you think is going to be most interesting, or any end goal years and years down the line that you would like to see this be put towards reaching. And you can discard the constraints of reality, Star Trek teleporters or something.
In some sense, you could ask how applicative are these bounds, which is almost an equivalent question to how near future we would have quantum computers which are classically interactable. But in some sense, apart from this open quantum system, the quantum speed limits that we already explored are kind of the end of the story in this direction. So, of course, I'm not a prophet, but I don't see how very specific research of quantum speed limits progress a lot without its companion, which are full-fledged quantum computers. Because now it's like we proved the theoretical idea, the theoretical notion, and now it's ready to be used. It's waiting on the shelf. To be used, it's waiting on the shelf in some sense.
Now, this has taken a lot of very sophisticated equipment and very specific setup to conduct these experiments. Is it limited to just the investigation that you've done in the speed limit research, or are there other places that you could go with this?
We're physicists, so what we do is we play with our setups. That's what we do for a living. And we ran these measurements and found out results about quantum speed limits, but it was very intriguing for us to just let the system play for a bit longer. So not only ask okay, how far can this red marble get from the blue one, but maybe in our case it has some slope also on the other hand, and it will come back, and the evolution might be more complex, so it might have some revivals or some periodicity in it. And we took quite long traces of this whole evolution of the particle for longer periods, and this don't have a lot to do with quantum speed limits, but it's still very interesting measurement. And then we asked, okay, we have this very precise measurement of the evolution of the wave function of this atom. What can we do with it? And we ran and analyzed this measurement. And in fact, we found out that by fitting these long time traces of the overlap between the two colored marbles, we can extract a lot of information about the underlying state. Specifically, we can extract both the energy spectrum, so the underlying energy levels of the atoms, and the population in each level of the specific state. So this is something which is very unique. It's kind of holographic technique that we developed. And the reason we are so proud of it is actually it's very model agnostic. So you almost don't assume anything about the underlying state. You just give this long input, and by fitting this long input to some very simple functional form, you can extract both the energies and the population, which is something very useful when we try to do quantum state analysis.
If people want to know more, where can they find your paper? And if they want to follow your research across quantum computing and anywhere else that your research leads you, where can they find more from you personally?
Sure. So I hold my personal publication record at personal website, galness.github.io, and there you can find basically all I published and also links to short talks about the different papers. It might be interesting to you. And if you are interested in this kind of subject, I very much encourage you to click on the very first link that takes you to Yoav Sagi's group website, my PhD supervisor, which perform a lot of fascinating experiments in this direction of science.
For anyone who does want to follow up on your website, the TLDR summaries that you have for all of your papers are tremendously informative and simplify things in a very accessible way. Thank you so much for those. Dr. Ness, thank you so much for your time today, and look forward to speaking to you again sometime soon.
Thanks a lot, Will. It was a pleasure.